Would someone be willing to give us a prayer for this Tuesday? Thank you.
Dear Father in heaven, we're so grateful for this beautiful day, and we're so grateful for all the blessings and great things we've received. And we're grateful that we're here at class safely. And Heavenly Father, please help us have thy spirit with us as we will be having our class. And please bless Dr. Francis as he will be teaching us. And please help us so that we'll be able to understand and remember the things that we'll be teaching. We'll be learning, and please bless the rest of our day with many great blessings and miracles, and help us find joy in everything that we'll be doing. And we say all these things in the name of Jesus Christ. Amen.
I am so grateful for your prayers. When I feel the Spirit during those prayers, it calms my nerves and gets me where I need to be. This was the average for exam 1A. And you remember we had a whole lot of perfect scores, more than I'd ever experienced before. We had a whole lot of A's, and I was thinking, boy, that's as good as it gets. But I was wrong. It turns out that after we took exam 1B, the average for the class went to 90%. The number of A's went to 445. The number of perfect scores went to 112, at which point I felt embarrassed. But most important, the number of failing grades dropped. And so I think that second exam showed that we made a lot of progress. If we look at who took that second exam, only half of the class took both exams, and that was largely due to the fact that so many people did well on the first exam that they didn't need to take the second exam. We had 93% of the class take the first exam, and then only half of you took both. Of those that took both exams, 90% of those students increased their score by an average amount of 16.5%. So give yourselves a hand, folks. You did well. Are there questions about the way we take exams in the course? Does that work for everyone? Okay. We're starting a new topic today, and this topic of electric charge, well, let's just find out. How many of you have studied electric charge in a previous life, you know, in elementary school or middle school or high school? Everyone's hand should be up. Come on. You know you did. You know you did. Okay. Now, I feel an obligation to teach that in a way that's a little bit different than you learned in middle school. And I will do that. The reading for today was section 16:1 through 16:3. And the reading for Thursday would be 16:4 through 16:5. Okay. Now, we're going to do some quick experiments. What we find is that if we take a rubber rod and we rub it with simulated cat fur, no cats were harmed. And if I put that on this little swivel here, and then if I take another rubber rod and rub it with a simulated cat fur, what I find is that they repel each other. Okay. Now, I also find that if I take a And I wasn't the one that invented this. This was Ben Franklin. He did these experiments first, and what he found was that if he took a glass rod and rubbed it with silk. Now, I don't have silk. I've got this piece of plastic that works the same as silk. But if I do that, what I find is that it attracts the rubber rod. Okay. And if I take another glass rod and charge it the same way that I did the first, what I find is that they repel each other. Pretty much the same as magic. Okay. Now, that's what you dealt with in junior high. Let's go one step further. If I take a wooden rod and charge it, and you don't charge it with fur or with silk, you charge the wooden rod like that. Okay. Now, the question I have is that what's going to happen to these guys when I bring it close? Talk to your neighbor. What's going to happen when I bring this close?
Are you? Yeah, I think. Whatever. You know, like.
Okay, let's find out.
I don't.
Okay, if I bring it near the rubber rod, let's make sure that we've got a charged rubber rod here. It attracts the rubber rod. Would you say that attracts the rubber rod? Okay, the people in the back don't know, but they chose to sit back there. That's their own fault. Okay. Now, predict what it's going to do with the glass rod. Talk to your neighbor.
No.
Wait, where's the
Okay, let's find out. When I bring it close to the glass rod, it attracts. Whoa. Allura Mora. Okay. Now, so with the wood, it attracts to both the rubber and the glass. And so now I want you to predict what's going to happen if I have two wooden rods charged up. Talk to your neighbor now. Thank you very much.
I agree. You like. I'll get it done.
Or a pen.
They all the other two repelled. It was.
Okay, let's find out. Nothing. They're two wooden rods, people. Come on. Can you imagine what would happen if two rods repelled each other? All the trees would be like, okay, no, they don't do anything, okay? They gar nix, the Germans would say, gar nix, okay, nothing. And so what you see is that one of these things is not like the other. And we can put everything in the universe into one of these three categories. Everything in the universe electrically acts like the rubber rod or the glass rod or the wooden rod. And most things act like the wooden rod, okay? Now, we treat that category separate because it acts differently. And we call that, the other two we call charged, and we call the wood neutral. Neutral, okay? Now, I think what surprised a lot of you was that the neutral object, the wooden rod, was able to attract the charged objects. Or if I turn that around, the charged objects were able to attract the neutral object, okay? Now, Ben Franklin, bless his heart, he gave us so many wonderful things, but not everyone's always right, okay? Ben had a 50-50 chance of getting this one right, and unfortunately, he got it wrong. He chose to call the rubber rod when it was charged negative and the glass rod positive. Now, his reason for doing that was that he believed that this charge had to do with this invisible essence, this stuff that somehow was contained by objects. And an object like the rubber that was missing some of the stuff, the essence, he felt that's what caused it to be charged and to exert these forces. And he felt that the glass had extras of these, this essence. And we're going to find out that he was just 180 degrees off base. See if your neighbor has learned about that before.
Like they were actually. But like,
Okay.
really care to look.
So let's talk about magnets. I think you all know that with magnets, if I have two north poles, they will repel each other. And if I have two south poles, they will repel each other. And if I have a north pole against a south pole, it will attract. Whoa, come back. Okay. So my question for you is, electrically, what's going on with this magnet here? I said earlier that everything could be put into one of these three categories. Electrically, it either acts like a charged rubber rod or a charged glass rod or a wooden rod. So does this act like a charged rubber rod, a charged glass rod, half rubber, half glass, or a neutral wooden rod? If you'll get out your clicker. Okay, now you can click.
Yeah. Yeah. Most of you.
Drop a magnet, it stops being a magnet. You drop it on a hard surface, you have to remagnetize them after. Thank you. Okay. Is that all of us? Everyone's voted? Okay, we said half rubber, half glass. Let's find out. Let's find out. So if I take the rubber rod and charge it up, I find that it attracts the South Pole and it attracts the North Pole. If I take the glass rod and charge it up, I find that it attracts the South Pole and it attracts the North Pole. And if I take the wooden rod and I charge it up, garnets, absolutely nothing. So what is this acting like? What's the magnet acting like? Like the wood, okay? It's acting like a neutral wooden rod. Electrically. There's something else going on there, this magnetism that we'll talk about in the last part of the class, but it has nothing to do with the electrical force that we were seeing before. Electrically, the magnets are acting just like a neutral wooden rod. Now, a question was asked while people were voting, and that is that, you know, the charge on these things, the rubber rod and the glass rod can dissipate. And I've got to tell you, this charge that gets on these rods, it can leak off if there's humidity in the air. And so when I was teaching many years ago in Seattle, this demo right here was the scariest demo in my semester. Because once I charged those rods, I had exactly 3 seconds to do the demo before they were neutral again, before they lost their charge. But here in the great state of Utah, it's so dry, you know, tomorrow they're still going to be charged up. Now, those of you that are going to be science teachers, high school, middle school science teachers, first of all, I love you more than the others, much more than the others, okay? You're the ones that are going to make a big impact. The other people are just going to do heart surgery, okay? But if you are doing these demos and nothing works right, what you need to do is just take those rods back in the back room and wash them with soap and water and dry them. Because it turns out that if you touch the rod, the oils from your hand coat the rod, and then that will make it very difficult to charge the rod. And in Montana, we had a demo guy that, you know, he was pretty protective of his stuff, and he would write down here, touch only this end in big capital letters. And he wanted to put touch only this end stupid, but we told him that wasn't appropriate. But eventually we all ended up grabbing the rod by the wrong side, and then we'd have to wash them again. Okay. Find out if your neighbor is going to be a high school or middle school science teacher. If so, kiss him on the lips. Okay. I think that we've all been exposed to the basic model of atoms, that we've got a nucleus that's made up of protons and neutrons, and the protons are positively charged like the glass rod. And swarming around this are a bunch of electrons that are negatively charged like the rubber rod. And that's a very simplified, outdated model. We now with quantum mechanics, we believe that it's more a probability cloud of where those electrons are. But this is the idea that we need for this class. And our modern view is that charge comes in two flavors, positive and negative, and that most things in the universe are neutral, by which we mean balanced. They have just as many protons as they have electrons, and the protons have the same charge as the electrons, just the protons are positive and the electrons are negative. And the amount of positive charge, that's in the nucleus. And the nucleus, you remember those protons are 1,800 times heavier than the electron. And the only way you can get rid of protons is to, take the rubber rod and take a saw and cut off part of it, get rid of some of the atoms. It's the electrons out in the orbits that we can either remove or add extras of. And that imbalance is what we call the net charge, or sometimes we're just sloppy and say, that's the charge, that's the charge. And so in our view, a neutral object would have just as many protons as electrons, just as much positive charge as negative charge. And then if we add negative electrons, well, that makes it negatively charged. Now, do you see that that's exactly opposite of what Brother Ben Franklin was telling us? Okay, he thought that the negative objects were the ones that were missing some of this essence. Well, the essence turns out to be electrons, and the negative charged objects aren't missing electrons. They've got extra electrons. Now, why does that matter? Well, it matters a lot, okay? When we get to electric circuits, we're going to have to jump through some mental hoops, play some games with ourselves just to get rid of some minus signs. Thank you, Brother Ben. Thank you. But it is what it is, okay? So that extra amount we call the net charge. Now, if we go back and start with a neutral object and we remove some of those electrons, what we find is that we've got some naked protons, some protons that don't have an electron, and that gives us a net positive charge, a net positive charge, okay? Now, I got to tell you something. I discovered that, ooh, that's fun. Nope, can't do that. Let's do this. Does that make you dizzy? Okay. So I discovered that on Apple products, they have something called live caption. And I tried this on my 8-year-old iPad, and it was just, it was awful. It was awful. But now it's getting pretty good. And so I'm going to use this to try to hear your questions. In class, I'm going to have this up front. And when you ask a question, Brinley, ask a question. Brinley's in the afternoon class.
What's Coulomb's,
Thomas, ask a question.
Coulomb's law?
Ask it louder.
What's Coulomb's law?
Everyone's law?
Coulomb.
True law? Okay, this is still not perfect, is it? Okay. I may have wasted $1,000.
Coulomb's law.
Oh, what's Kuban's law? Kuban's law is only true in other parts of the universe, not here. Okay. Kuban's law. And when I said it, they spelled it with a C, and when Thomas said it, they spelled it with a K. So this is not working.
So
Now,
Professor, might not only work with names. It might not only work with names. Abnormal names.
well, I know there are other programs, and I'm going to explore those and see if we can get one that works. I found one that works pretty good. They just want $20 a month, but I think in for a lamb, in for a sheep. Okay. In this week's tutorial, we're going to do some experiments. I'm going to do the experiments in the video, but you can follow along at home. The experiments are really quite simple, and all they require is some Scotch tape. And I think most of you have Scotch tape in your apartment. And what you're going to do with that Scotch tape is you're going to, first of all, fold down a little piece of it at the end so that you can peel it off of your tabletop. And then what you're going to do is you're just going to put that down on the table and rub it. Okay. And then you're going to make another one of those. Again, if you don't want to spend the rest of the day scraping off tape, you want to fold down a piece to make a handle and rub that. And it turns out that that tape and the tabletop have different affinities for the electrons. In other words, one of them wants them more than the other. Okay. And so if I treat both of these the same, what I find is, first of all, they attract to my hand. Why is that? Tell your neighbor.
Yeah.
No. On the front.
Okay. I hope you said Greg's hand is neutral, like the wooden rod. If these guys are charged, they're going to be attracted to a neutral object. Now, when I bring them close to each other, you see that they repel each other. Let me do that again. They touched my hand. There, you see, they are repelling each other. Is that in? Yeah, they're repelling each other. Now, the next experiment we're going to do is we're going to put those on top of each, one on top of the other. And we're going to make another set. Put one down and put another one on top of it. And then we're going to label them with your pen, one top and one bottom. And I'm going to rip these off together. And then I'm going to separate them. Okay. First, I'm going to kiss them so that this is neutral. But now I'm going to put the one on the bottom over here and the one on the top close to you. Okay. Now, predict with your neighbor what's going to happen when I bring a top towards the top, a bottom towards the bottom, top towards the bottom. Tell your neighbor.
Right?
What you mean? Yeah, that's right. What happened? Yes.
Rubbing together, maybe then. Sorry.
Okay. Let's look at the bottom of the bottom with the bottom. I think you can see that that's a repulsion. And the top with the top, that's a repulsion. And the bottom with the top is an attraction. Okay. And so it turns out that when I rip them apart, one of those pieces of tape has a greater affinity for the electrons than the other. Well, Greg, they're both the same. They're both tape. Well, except the place where they're touching each other, for the top tape, it's the sticky part that's touching. And for the bottom tape, it's the smooth part that's touching. So they're not the same surfaces. And one of them wants those electrons more than the other. When we do some experiments with the charged rods, what we find surprisingly is it's not the sticky side that wants the electrons the most. It's the smooth side. Talk to your neighbor. See if your neighbor is really excited for this week's tutorial.
Wait. Yeah, it's here. Where's the where they
The light. I don't know. He's
Rap.
Okay. So when I charge up a rod, how many electrons am I taking away from the glass rod, and how many electrons am I typically giving to the rubber rod? Well, it turns out it's kind of like 100 million. It's a lot. It's a lot. But compared to the total number of electrons in that rod, it's a negligible amount. Now, this seems kind of out of the blue. This seems kind of apropos of nothing, but I promise you it's important. If a bushel basket contains 50 apples, how much of a bushel is just one apple? Tell your neighbor. How many bushels do you have when you've just got one apple?
Looks like these. Size of the apple matter quite a bit.
My sister's. It's just a bit wrong.
Okay.
Yeah.
You have 1/50th of a bushel. That makes sense? 1/50th of a bushel. Hold that thought. Hold that thought. When we measure charge, we measure it in units of coulombs, or coulombs if you believe the iPad. Coulombs. Again, to honor a dead physicist. Okay? Coulombs are big. A coulomb is a whole lot of charge. It's the charge contained in 6.25 times 10 to the 18 bare protons. more visual example would be if I had 1 coulomb here on the table, we're all dead. Okay, we've destroyed the building. Okay, that's a lot of charge. And that will exert a lot of force. Now, why do we use a unit that's so large? Well, the unit that was defined first was the ampere. Again, the name is to honor a dead physicist. 1 ampere is a reasonable amount of current. That's how much current you would expect to be running through a household appliance. Okay, some fraction of an ampere. Now, the ampere is 1 coulomb of charge passing through a point in the wire each second. Okay, so even though 1 amp is not an unreasonable amount of current flow of charge, it takes a whole lot of actual charge going through to make 1 amp. Okay, and so we got stuck with this huge, enormous unit, the coulomb. Now, what is the charge on a single proton? Go back to the bushel of apples, talk to your neighbor, get out your calculator, and figure it out. What's the charge on just 1 proton? What's the number of bushels of just 1 apple?
Oh, yeah. We even need.
One time 6 and 8.
Okay. If it takes 6.25 times 10 to the 18 protons to make 1 coulomb, the charge on a single proton is going to be 1 over that number, 1 over 6.25 times 10 to the 18. And if I put that into my calculator, what I get is 1.6 times 10 to the minus 19, and that would be coulombs per proton. And we call that the elementary charge. And we give it the symbol little e. Now, here's an unfortunate coincidence. It turns out that elementary starts with the letter E, and so does electron. And so a lot of people, when they're starting their study of physics, get confused, and they think that that E is the electron charge. Absolutely not. It's the proton charge. It's the elementary charge. And the electron actually has a charge of negative E. Okay, so I would have a positive 1.6 times negative 19 coulombs on a proton. I would have a negative 1.6 times 10 to the minus 19 coulombs on the electron. Now, folks, I'm an old man with some sad stories to tell, but I have run into a whole lot of people who got high centered on exams because they weren't sure how to figure out the charge on this particular electron. And no, it's not. This electron's no different than any other electron in the universe. They all have the same charge. It's that number, 1.6 times 10 to the minus 19, and that number will be on the front page of your next exam. You do not need to memorize it unless you want to go to a geek party and be taken seriously. Okay, if you want to go to a geek party, you better know that number. Okay. Questions on that? Okay. So a penny contains about 2 times 10 to the 23rd protons and an equal number of electrons. Hence, it's neutral. It acts like the wooden rod. If the penny is charged to 1 coulomb, at which point it kills us all, what fractions of the electrons have been added or removed? First of all, am I adding electrons or removing electrons? Shout it out. You're removing electrons. to make it a positive 1 coulomb. And the fraction is just going to be the number removed divided by the original number of electrons that we started with. And we were told the original number is 2 times 10 to the 23rd. Okay. Now, in order to make that charge on the penny 1 coulomb, I have to remove 6.25 times 10 to the 18 electrons. Now, we've got this law, not Kublan's law, but it's called Lee's law of large numbers. And that is, for humans, all large numbers seem the same. 10 to the 18, 10 to the 23rd, you know, it's big. But in truth, there's big and then there's way big, okay? And so this, when we divide it out, is 3/1000ths of a percent. And so a very, very tiny fraction of the electrons are removed. And that's to charge it up to 1 coulomb. What I was doing up here was charging things up to what we call a microcoulomb or a nanocoulomb. And let's just be clear what that means. A microcoulomb is 10 to the minus 6 coulombs. A nanocoulomb is 10 to the minus 9 coulombs. And those are the types of charges that you're going to see in real life. In the homework problems and things like that, we'll use microcoulombs and nanocoulombs. How many of you have seen that notation before? Okay. Yeah, you're all going to be doctors. You've seen it. Okay. Now, you've also learned, I hope, about conductivity. That there are some things called conductors, they tend to be metal, where the valence electrons, the electrons that are in the outer shells of the atom, are free to wander. Okay, they're free to move from atom to atom as they feel so pushed. They charge flows freely. But in insulators like the wooden rod and ceramics and plastics and things like that, the electrons are all tightly bound to their own atom and they don't go wandering anywhere else. And so we're going to talk about these different objects. I've got here a can, and this can is neutral. How do you know it's neutral, Greg? Because I'm holding it in my hand. And if there were too many electrons on this thing, they would want to get as far away from each other as possible. And I'm a conductor, it's a conductor, I'm holding it. If there were extra electrons in this, they would spread onto me to get as far away from each other because I'm much bigger than this can. That's another way of knowing that this magnet is neutral because it's iron, it's metal, it's a conductor, and I'm holding it in my hand. It's neutral because any extra electrons would want to get onto me. I'm much bigger, okay? Now, if I take this can and take a negative charged rubber rod, come on back. Taking my can for a walk. Whoa, no, don't think it's. Okay. Now, if I did that with a glass rod, again, okay, I touched it. So let's make it neutral again. Okay, let's talk about what's going on there. I can model that can as a whole bunch of positive charge and negative charge. And if it's neutral, I've got just as much positive charge as I've got negative charge. Yes, sir.
What if it's
Well, what?
what if it's full?
Oh, if it's full, it's got more inertia. It's still neutral. It's just gonna move slower. Yeah, I always use the empty can so that it'll work. So that's how I model this neutral can. And if I bring ebonite's a fancy, sophisticated word for rubber rod. If I bring this rubber rod nearby that's got way too many electrons, what I find is that the negative charges in the can are repelled by the negative charges in the rubber rod. Okay. And but what about the positive charges? How do they move in the can? They don't. The positive charges, remember, are in the nucleus, and that's tied into the lattice work of the metal. That they don't go anywhere. The positive charges don't move. Okay, it's the negative charges, the electrons, that move, and they're going to be repelled by the rubber rod away from the rubber rod. Now, as I look at that picture, I see a problem. Do you see a problem? Those negative electrons don't want to be near the rubber rod, but they also don't want to be near each other. Okay, it's like you get a bunch of people in an elevator, they're not going to all end up in one corner. Okay, they're going to spread out. Now, what's really going to happen is that rubber rod is going to shift the electrons in the can just a little bit. Okay, they're all going to take a baby step to the left. Okay, but by doing that, we find out that there's a part of the can, the part closest to the rubber rod, that is now more positive than negative. And there is a part of the can, the part further away from the rubber rod, that is more negative than positive. Okay, and so that positive side of the can is going to be attracted to the rubber rod, and the negative part of that can is going to be repelled from the rubber rod. And I've got just as much negative charge over here as I've got positive charge over there. So those two forces, would they be equal? No or heck no.
No.
Yeah, we saw that they weren't because we got a net attraction. So why is this repulsive force on the negative charge smaller than the attractive force on the positive charge? Tell your neighbor what the answer is. What's going on there?
Rubber can get it. So. Oh, brother.
Art balance. Still low. What if we mess that scrimmage?
Okay. I hope what you told your neighbor was, well, this electric force, this attraction or repulsion, it's dependent on distance. And the negative side of the can is the far side of the can, the part of the can that's further away from the rubber rod. And so that force, that repulsive force, is going to be smaller. And so the net force is going to be an attractive force. Now, if I had used glass instead, well, now the glass rod's positive, and that means all of the electrons are going to shift to the right. And that means the attractive force is going to be with the side of the can that's closest to the glass rod again. And so I get an attractive force whether I'm using a negative rubber rod or a positive glass rod. It doesn't matter. And that's the same thing we saw with the wood. It was attracted to either rod. Now, I popped that balloon. Let's try not to pop this one. Okay. Now, if I were to rub this on simulated human fur, oh, you've done this before, right? You've done this before. Thank you, sir. He's the man. Okay. So that wooden door is obviously a non-conductor, an insulator. Okay, it's not metal. And so what's going on there? Well, if I look at the door, it's made up of molecules, and those molecules are neutral. They've got just as much positive charge as negative charge. But they're not in general symmetric. Usually, often, what we find is that those molecules have one side of it that's more positive and another side that's more negative. You learn about that in your chemistry class. And when we bring a rubber rod that's charged, or in this case, a charged rubber balloon, okay, what we find is that the electrons aren't free to just swim where they're happy, to their happy place. They're tied to their molecule. They're not going anywhere. But usually we can get those things to rotate, okay? Or we can get the negative side to move away. And the closer we get that balloon, or in this case, the rubber rod, the more of those molecules rotate. Now, what we see, if we look close to the surface of that door, is we see more positive charge than negative charge. Okay. Now, if these people in the middle, let's imagine that you are each a molecule of wood. Okay. And your head's positive because it thinks, and your feet are negative because they stink. Okay. And so this is a negatively charged rod, or negatively charged rubber balloon. And so when I bring this close to all of you molecules, how are you going to lean? Your head's positive and yeah, okay. You lean, come on, lean, people, lean with me. Lean, good. Okay. Now, what I see over here on this side of the door is a whole bunch of heads sticking out, a whole bunch of positive charge. On the other side of the door, I see a whole bunch of feet sticking out, right? So I've got a surface charge of positive charge and a surface charge of negative charge over there. But again, this charge over here is closer to the balloon. And so I get the attraction. See if your neighbor has stinky feet.
Someone's tell you.
Sister. We go on family trips and she take off her shoe. So bad.
Okay. I'm not sure if this is going to work. I grabbed this swivel right before class, but I've got a piece of lumber on there, and I've just got a big positively charged rod, and let me see if I can. Come on. There it goes, there it goes, there it goes, there it goes. Oh.
I think I wondered.
Okay. That's convincing, I think. Now it comes the other way. Okay, that worked. That could have been bad. Okay. Now. So in summary, for a conductor, the charge flows to where it's happy, and an insulator, the charge just shifts. But in both cases, whether it's a conductor or an insulator, if it's neutral, it will be attracted to both positively charged objects and negatively charged objects due to this shift in charge. Okay, so let's do a check question to see if we're all on the bus here. You remove one electron from a quarter and one electron from a Buick. A Buick used to be a car. Which, if either, has the greater charge, the quarter, the Buick, or neither? Let me get you started. Now you can click.
There we go. Very simple. This. I like that.
I get it. That's only
It's like maybe
yeah. Yeah.
Okay. This is not rocket science. We did rocket science in 105. Okay, I'm calling it last call. Good, good. Most of you are understanding this. If I take one electron from either one of those things, I've only left one naked proton behind. They both started out neutral. The Buick has a whole lot more positive charge and negative charge than the quarter, but they both have the same positive charge as negative charge. And if I take one electron away, I just have one naked proton in both cases. So they both have a net charge of 1.6 times 10 to the minus 19 coulombs. So the answer is neither. Okay. I want you to see charge as a property of an object. Okay, if I have a rubber ball, I would say that the color of that ball is blue. That's a property of that ball. The shape of that ball is round. That's a property of that ball. The mass I measure to be 2 kilograms, okay? And because it has that mass, it can exert a gravitational force on everything else that has mass. But that mass of 2 kilograms is just a property, a way of describing that ball. I can also say that the charge of that ball is -2 microcoulombs. Well, what that tells me is it's got too many electrons, more electrons than it has protons. And I could quickly figure out how many extra electrons, okay? And because of those extra electrons, because of that net charge, it can exert forces, electrical forces, on other objects. Now, it turns out that that electrical force looks a whole lot like the gravitational force. You remember that the gravitational force we said was an inverse square force. In other words, if I had any two masses that were separated by a distance r, that force between them depended on 1 over r squared. And that meant if they were twice as far away, the force would be 1/4 as strong. If they were 3 times as far away, the force would be 1/9 as strong. 4 times as far away, 1/16 as strong. It very quickly drops off with distance. And it's proportional to the product of the two masses. And of course, this is the constant of proportionality that Henry Cavendish gave us with his incredible experiment many, many years ago. Now, because that depends on the product of the masses, well, first of all, that's the force on either one of those. Newton's third law was built into Newton's law of gravity. If one of those has a huge mass and one of those has a small mass, it's the product of the two masses. And 1 times a million is the same as a million times 1, right? And so I have exactly the same force on the rocket ship as I have on the Death Star. Equal and opposite by Newton's third law, equal and opposite by the law of gravity. The law of gravity. Now, it turns out that the electric force follows Coulomb's law. Coulomb's law. Coulomb's law. And it has exactly the same form as the gravitational force. Again, any two charges separated by a distance r, the force depends on 1 over r squared. Twice as far away, 1/4 as strong, and so forth. Now, the big difference between this force and the gravitational force is that the gravitational force is always attractive, whereas this electrical force can be repulsive or it can be attractive. We found that if Q1 and Q2 have the same sign, if they're both positive or both negative, this is going to be a repulsive force away. Now, that constant of proportionality we call Coulomb's constant, and its value is really easy to remember. It is 9 times 10 to the 9. Okay. And that's going to be on the front page of the exam as well. Now, if you look at that law, Coulomb's law, and you ask the question, what if Q2 is equal to 0? What if that second object is neutral? What does Coulomb's law predict for the force between that charged object and that neutral object? 0. Okay. Anything you multiply by 0 is 0. But that's not what we saw in real life. That is not what we saw in real life. And that points out a very important aspect of Coulomb's law. And that is that it only applies to point charges, okay? What do you mean by a point charge? How small does it have to be, Greg? Well, the object has to be small compared to the distance between them. I could have a charged Volkswagen in Provo and another charged Volkswagen in Springville, and those would obey Coulomb's law because they're very small compared to the distance between Provo and Springville. Okay, but when we were dealing with this glass rod and this wooden rod, I had them really close to each other. Okay, and we found that Coulomb's law didn't give the right answer. It only works with point sources. Now that makes it different than the gravitational law, which by calculus, Newton was able to find we could do that with the Earth, even when we were close to the Earth. And it was definitely not a point mass, but we could pretend that all of the mass of the Earth was concentrated at the center of the Earth. And that's because all of the mass is positive. Whereas with charge, we've got positive and we've also got negative. And that undoes that symmetry that we had with the gravitational force. See if your neighbor's still on the bus, please.
You know what that means?
That's true.
Okay, let's try one more clicker question. 2-point charges attract towards each other with an electric force of magnitude F. If the charge on one of the particles is reduced to 1/3 of its original value and the distance between the particles is doubled, what is the resulting magnitude of the electric force between them? Go ahead and click. I hope this is obvious to everyone. I hope that this is an easy question.
Yeah, that's what I'm saying. One.
Okay, get it done.
Yeah.
I don't know.
That's already 1/3 of the throw. Goes from point.
Slightly new. Not at all like what we just given.
Okay, last call. Think we're missing a few people. Okay. Good, the answer is A. The answer is A. Okay, folks, if I start the next topic, we're gonna end right in the middle of an important idea. So let's stop here. Make sure you get over there to the devotional. Today it's Elder Shumway. Next Tuesday, it's the prophet. President Oaks is going to be speaking next Tuesday.
No, you just let us out.
Well, if you look at the port, it depends on the charges. And one of those charges got to be 1/3 as big. It also depends on 1/over the distance squared. And so if the charge stayed the same, the force would get 1/4 as strong due to the distance. If the distance stayed the same and the charge got 1/3 as big, it would get 1/3 as strong. You combine those, you get 1/4. Turn something off here.